We're now moving into the last chapter of the course and the last main topic, and that involves the area of chemical reactions. So if you recall from one of the very first lectures we had in the course, that's where we introduced the topic of thermodynamics. I just want to recall that now and we'll take a look at it. So that was the definition that we used for thermodynamics. So what we were talking about, we said that it is the study of energy transformations. And so we spent a lot of time looking at energy, heat in, heat out, moving heat around with heat engines, things like that, or refrigeration cycles. And it also involves relationship among the physical properties. So we spent a lot of time looking at property data. That's what helps us do our calculations. Of substances, those would be the working fluids that are affected by these transformations. So that was our definition of thermodynamics, but no place in the course have we yet defined where the energy is coming from. We haven't really said much about energy or where we are getting the energy from. So what I want to start with this lecture is by looking at where do we get energy from? So that's kind of a central point that we need to take a look at. So let's now spend a couple of minutes looking where energy comes from. And what I'll begin by doing is giving you a slide. This is data that has been prepared by the US government. And what it is showing is primary energy consumption estimates going back to the late 1700s all the way up to 2010. So what we have is oil, gas, and coal. And so you can see those three are right now the primary sources of energy that we are using. Further down we have nuclear, and then we have other sources such as wind, hydro, and other renewable energy sources. Now, some things to note in this chart. First of all, in the about 1973, the price of oil went up because of oil embargoes, and so within the U.S., oil prices skyrocketed as they did globally. People were weaned off of oil as a result of that, partially because of the economic slowdown, but also because they found other technologies, and that will explain this drop here. And then we see another drop up here starting in about 2000, mid-2000s. That's related to the economic crisis that started in about 2007. And consequently, that gives us an idea as to the energy use. But the main thing to take off of this is that where are we getting our energy from? Well, for the most part, we're getting it from oil, gas, and coal. So those are the primary means by which we're getting our energy. There's another diagram that we can look at, again prepared by the US government at Lawrence Livermore Laboratory. And what I like about this diagram, it shows over on the left-hand side the different sources of energy, where we are getting the energy from. And then it shows us where we are using that energy. So either we generate electricity with the energy, and then where is that energy going to go? Well, some of the electricity that is generated goes into residential, some goes to commercial, some goes to industrial, and a very, 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 very small fraction will go into transportation. That would be things like the Tesla car or the Volt plug-in hybrids, cars like that. So, but the other thing to note here, let's consider electricity generation to begin with. You'll notice that with the electricity, we have all of these different inputs. So we have an input due to nuclear, we have an input due to natural gas, we have an input due to hydro, and an input due to coal, the energy that is coming out of that, we see here 12.6 quads is shown, plus another 26.6 goes into waste heat. If you recall, whenever we looked at a heat engine cycle, we always have to have some energy rejected to the environment, and that is the energy being rejected to the environment. So let's just take a look at electricity as an example. And looking at the numbers that we have here, we have 39.2 units of energy that we're showing is being for electricity production. The amount of real work that we're getting out of that is 12.6. So let's say electricity. What we have is 12.6, and this is in terms of quads. And I'm now going to divide it, that's what we're getting as the output. I'm going to divide what we're putting into that. And I'm going to remove a couple of the different sources. The ones that I will remove will be hydro and wind. And so we have 39.2 quads. 39.2, and I will subtract off the amount due to hydro, which is 3.17, and I will subtract off the amount due to wind, which is 1.17. The reason why I'm subtracting those off is because what I want to do is I want to get a quantification in terms of the efficiency of electricity production. And nuclear operates on a form of the Rankine cycle. Natural gas for electricity generation would be a combined cycle, so you'd have a Brayton cycle along with a Rankine cycle, and coal most certainly will operate off of the Rankine cycle as well. So in a way, this kind of gives us a global estimate as to the efficiency of the Rankine cycle for electricity production. And when you do the math here, what you get is 36.2%. So in terms of U.S. energy production, typically the Rankine cycles that they have are efficient on the order of about 36.2% for electricity generation. Now we can do the same thing for transportation. So looking at transportation, what we have here, the energy useful work coming out, or energy coming out, is 6.76. And I'm going to now divide that by the input, which I'll say the input is 27 quads, because we have input coming from petroleum. And the other place where we have input, we have a little bit of biomass. Maybe I should subtract that off, but I won't. And we have a little bit coming from natural gas. That could be compressed natural gas vehicles and things like that. So we have then for the input here, actually, you know what I'll do? Let me take off the amount due to biomass. So we have 27 minus 1.15, and we'll do the calculation. So let me grab my calculator here. So what we obtain here is 26.1% for the efficiency with the conversion for transportation. And what types of cycles would those be? Well, that would be auto, diesel, and the Brayton. So that gives us kind of a global estimate in terms of the efficiency of these cycles, and this one up here would be the Rankine. So that's the efficiency of these cycles in terms of just looking at overall energy use within the US. The last thing that I want to look at in terms of where do we get energy from is this diagram here. And what is interesting about this diagram is it shows us the supply sources. So this is where the energy is coming in. We have some coming in with petroleum, we have some coming in with natural gas, some with coal, renewable energy, so that could be hydroelectric, it could be wind, it could be solar photovoltaic, and then nuclear energy is down at the bottom here. But what I want to do, I want to look at the ones that involve chemical reactions. So petroleum will involve a chemical reaction because we would have to combust the petroleum. It would be in the form of gas or diesel. Natural gas would be combustion, and coal would be a chemical reaction, combustion. So when we look at this, what we find is that 37 plus 25 plus 21, we get a total of 83% of energy use is coming from carbon-based fuels, that in order to get the energy out of them, we have to go through a chemical reaction, and we call that chemical reaction combustion. And so that is what we are going to be looking at in this lecture. So what we can write, is that around 83% of energy consumed, now this is in the US, but about 83% of energy consumed is done so using fossil fuels and combustion. And this data was for 2009. So this would be an estimate for year 2009. So with that, we're talking about combustion, and sometimes we call that fire. And so it then becomes a natural question to say, what is combustion? What is fire? And so with that, I want to take a look at a couple of video clips that will help us get a better understanding in terms of what fire or combustion actually is. So to begin with, this is actually the boiler out of the steam locomotive that I showed when we looked at the Rankine cycle. And when you look in, and what we've done is a slow motion video of the boiler. It was oil being combusted inside of this boiler, but you can see the flames, and they're, depending on how you view it, very beautiful or very frightening vertical structures that are in that flame. Well, what composes those? So let's take a look at another video clip. This is a gravity-fed fluid flow, and what I'm going to do, I'm going to play a trick and flip the gravity vector on you, and then there you can see the fluid flow moving up, and what I'll do is I'll compare it on the right to the combustion fluid flow that we were looking at, and with that you can see very, very similar structures between the flames and the fluid flow. So what is happening, and the reason why you see the similarity, it's because what is fire? Well, fire is actually fluid flow with some other things going on. So to answer the question, what is fire? And technically I should say combustion, but I'll call it fire. What is fire? Well, first of all, it is a buoyancy driven, and that's why I flipped the gravity vector on that fluid flow in order to replicate a buoyancy driven fluid flow. So it's buoyancy driven fluid flow with chemical reactions, and we also, through those chemical reactions, have heat release. So when you have a chemical reaction with heat release, what that does is it drives the buoyancy-driven fluid flow. And so in a nutshell, in a very, very simple way, you could say that that is what fire consists of. It's a fluid flow with chemical reaction and heat release. Technically speaking, however, the fire is kind of the common word that we would use, but a more technical word would be combustion, or even more technical, we could say it is an oxidation reaction. So what we're going to do in this lecture, in the next few lectures, is we are going to take a look at combustion and oxidation reaction, and we will apply thermodynamic analysis to combustion and oxidation reactions in order to quantify what is going on through these processes. So that's where we're going. That's a bit of an introduction to combustion, fire, and oxidation.